Assalamualaikum warahmatullahi wabarakatuh, and I hope everyone is having a good day. My name is Narshada Zalim. I'm from University of Technology Mara, Malaysia. My main supervisor is Dr. Sitimas Liza from Faculty of Plantation and Agro-Technology, and co-supervisor is Professor Nadia Dr. Tan Hulang and Professor Nadia Dr. Nafija Gobakar from Faculty of Chemical Engineering. And today I'll be presenting on the topics of eco-friendly for product design by synthesizing and characterization of cellulose acetate and zinc oxide nanoparticles electrospun nanofiber as seed coating material for enhanced Arab pediceeds germination. As for the introduction, as we all know, paddy is an important food grain crop for more than 50% of the global populations, and the enhance of the global population by 2050 by 10 billion people will eventually increase the demand of this food grain crop. But we are facing climate change that can have a severe threat on the paddy production, and this will affect the food security of the world. Thus, we are focusing on the seed coating as a major approach in entertaining the agriculture's sustainability by enhancing the agronomic properties and especially on the seed germination in highly tropical countries and other regions. This study is focusing on the approach of nanotechnology in producing sustainable biopolymer based nanofiber, which an environmental friendly product design by the inclusion of minimal input application to enhance the crop germination and also development. Okay, as for the objective of this study, first we are focusing on synthesize the formation of the biopolymer with the inclusion of zinc oxide in the cellulose acetate nanofiber for the seed coating of aerobic paddy seeds. Next, we're going to characterize the nanometric properties of the nanofiber that we produce and study the diminution rate of the seed coating that we are applying on the aerobic paddy seeds. The approach here is using the electrospinning process to produce the nanofiber. The polymer solution that we are focusing here is cellulose acetate and also the zinc oxide nanoparticles. The solution that we produce can go through electrospinning process with the inclusion of high voltage power supply that can produce electrostatic force that can do the phase inversion from the solution to the solid of nanofiber. And this nanofiber will be used to coat the seeds. While we are focusing on the seed coating, because with the minimal input application, we can enhance the germination rates and also the crop development and reduce the losses because it is high efficiency rate of the input that we are focusing, and also reduce the environmental effects that being caused by over application of fertilizer and agronomic input in the agriculture. So why nanofiber? Okay, nanofiber here we have intraporosity and interporosity. Intraporosity is within or between the fiber, and interporosity is within the fiber. This projecting the enhance of the oxygen permeability of the nanofiber acid coating that favor for the seed coating for the seed germination. And also for as following here the molecular structure of the cellulose acetate, zinc oxide is bound to the acetyl group of the cellulose acetate and performing a complex structure, which is a packaging of the zinc oxide that we are going to use. And this eventually will produce control release behavior of the seed coating for the seed germination. The cellulose acetate nanofiber also have a high water absorption rate and high surface area to the nanometric scale size. The material that we are focusing here is cellulose acetate and also zinc oxide nanoparticles. Cellulose acetate is a biodegradable product and have abundant supply all over the world. And zinc oxide nanoparticles is an engineered material that comes within less than 100 nanometer scale size, and it supply as micronutrients to the seeds germination, and is also connected to the law of zinc supply in the agricultural soil. Thus, with the inclusion of zinc oxide, it can supply the micronutrients for the crop development. And also, zinc oxide is playing a role in the growth hormone production, especially for the seed germination, chlorophyll biosynthesis for the food production to enhance the crop development, and due to nanometric scale size, it can enhance the absorption rate that can easily uptake by the crop. The conceptual work and the methodology we are approaching here is firstly we conduct the seedability test, and then we can synthesize the formulation for seed coating by utilizing different weight of cellulose acetate and using binary solvent of acetone and water. We're gonna fix the electrospinning parameter as we can see here, and after that we can study the nanometric scale size properties of the nanofiber. Using the instrument of SEM for the morphology, you're gonna study the porosity and liquid uptake, FTIR, EDX, and water coating angles. And then we're gonna proceed with the seed coating through the electrospinning process and conduct the seed germination to study the germination rate between the control cellulose acetate nanofiber alone and cellulose acetate with the inclusion of zinc oxide nanoparticles with 100 mg per liter of concentration. So this is the method that we are utilizing, and here the seed coating method is by utilizing layer by layer coating method, which we're gonna electrospin the fiber on the aluminum foil, and then we're gonna place the seeds onto the fiber and produce more fiber on top of it. We're gonna punch and within a 5 meter scale range, and this is the image of the fiber coated seeds that we have been producing. As for the results for this study, we are utilizing different polymer weight of cellulose acetate and study within this concentration, which concentration are able to produce a good fiber. So eventually 12% and 15% percentage of nanofiber producing beads and ripple-like structure that caused by the non-evaporation of the solvent. And this is not favorable as it has high surface area and also microstructure. But eventually we are able to produce by 17 percentage of nanofiber that we're able to produce a uniform continuous fiber within nanometric scale size, which is 526 nanometer. Though with the inclusion of the zinc oxide nanoparticles, zinc oxide is increase the conductivity level of the solution. Thus, we are able to produce more finer fiber compared to cellulose acetate alone. As the FTIR and EDX studies to study the presence of the zinc and also cellulose acetate within the fiber, cellulose acetate have 4 functional groups, which is OH, COCH, and C-double-bond-O. And as we can see here, with the available peak and wavelength on the FTIR results, that's the presence of cellulose acetate. And for the zinc oxide nanoparticles, it's bond with the C-double-bond-O here. So we can see the stretching, high absorption and high stretching peak of C-double-bond-O. So this indicate the presence of zinc oxides. For the EDX study also, we're able to see the presence of zinc oxide nanoparticles. For the UV study is to study the kinetic release study of the zinc oxide nanoparticle from the nanofiber. We immerse the nanofiber for 24 hours, and the result shows that the presence of zinc oxide nanoparticle within the fiber that able to be released within 24 hours. As for the water contact angle, the zinc oxide nanoparticles, as explained before, decrease the fiber diameter and increase the hydrophobicity of nanofiber from 98 to 131 degree. It is favorable acid coating because with the hydrophobicity of the material, it's able to control the release of zinc oxide nanoparticles for a long period of time and reduce the toxicity effects. And for the porosity and liquid uptake test, as we can see here, compared to the cellulose acetate and cellulose acetate with the inclusion of zinc oxide nanoparticles, the cellulose acetate and zinc oxide nanoparticles nanofiber have higher porosity and liquid uptake test. This might be due to the porosity of the nanofiber and also the diameter of the nanofiber. With the finer diameter of nanofiber, more smaller scale size, the porosity is higher and the liquid uptake is higher. Thus, this is favorable for the seed coating element for the seed coating. Eventually, this is the result for the germination study. We can see here that an increase of 20% germination rate of the zinc oxide inclusion with the cellulose acetate compared to the control. I mean, there's increase of 20% germination rate compared to the control, and also 14% increase compared to cellulose nanofiber alone. As for the conclusion, this seed coating material from nanofiber have intra and interporosity that can enhance the osteopermeability and also have high water uptake, which is both important element for seed germination to increase the crop development and to enhance the seed germination rate of these aeroplaning seeds. And with the morphology and structure and properties of nanofiber, we're able to have control nutrient delivery system. Thus, the conclusion of this study, we're able to enhance the germination rate of aerobic paddy seeds through the application of cellulose acetate, zinc oxide, nanoparticles, and electrosperm nanofiber. So that's all from me. I enjoyed the slides. And thank you and have a good day.